What's up, guys? My name is Michael and welcome to my YouTube channel. Before you continue this video, please hit the subscribe button and hit the like button because I really need some subscribers. Yeah. Okay, so today we're going to talk about heaps and priority queues. And the reason why we're going to talk about heaps and priority queues, if you're wondering why, well, you need priority when you have a data structure. Sometimes you want things you want things to be in order, like not in order, but like have, regardless of the order, you want to have someone special in a line. That's what a priority queue is, basically. Someone has better priority than another person. Like the rock stars. Like when you're waiting in a club at a restaurant, some people get served first, all right? Even if you don't like it, well, that's basically what this data structure is. It gives priority for, just like what is priority queues. And heaps are basically the same thing. Well, heaps are the same thing as binary search trees, except they have a certain kind of element that's really good about it, and I'll tell you it sooner or later when we get into it. So before I continue, please hit the subscribe button and hit the like button because I really need some motivation. We hit 18 subscribers, and I really like that. So yeah, I actually really like the fact that like people are watching. I really like the fact that people are watching because no, sometimes like I just get demotivated. And if you're wondering why I didn't make any videos for the past 3 days, it's mainly because like I was doing a programming contest. It was on CodeSheet. You guys, you have to do, in order to like use these data structures, you have to do some online programming competitions. Competitive programming. They use a lot of these data structures. Another thing, you could just do the exercises in these books, but it's not really that fun. But I'll continue those exercises sooner or later. But yeah, we're going to talk about priority queue. So what is a priority queue? So a priority queue is basically an abstract data type that allows you to store collections of elements that supports insertion, but also supports removal of elements in order of priority. So it supports like arbitrary element insertion. So that could mean any order that you want to insert, but also allows removal of elements in order of priority. So elements with first priority can be removed at any time. This is basically different from the other data structures we had because they were like, although like queues, stacks, queues, dequeues, lists, trees, because they were based on positions, specific positions, and the positions in the elements were determined by the insertion and deletion operations performed. So the positions in the linear arrangement of the elements were determined by the insertion and deletion, and these are not the same in priority queues. In priority queues, they store elements according to their priorities, not by like positions or anything. So let's talk about keys, priorities, and total order relations. Um, so let's talk about keys, priorities, and total order relations. And what exactly do I mean by keys? So basically, a key is a way to rank an object to another object to compare them both. It's a certain attribute or property for two objects to have, and it's a way to it allows you to compare and rank these objects according to parameters or properties. That's what I mean by a key. When a key to an object that is assigned to an element is like a specific attribute for that element and can be used to identify that element. Okay, it's just like one specific thing that could allow you to identify an element. It's like compared to the other elements. Like it's a special thing. That's what I mean by the key. That's what a key is. It's like a unique thing for that object. Note, when a key is assigned to an element, typically by a user or application, a key might represent a property that an element did not originally possess. So when you assign a key to an element, that key might not have been there before. Like that object, that specific attribute that you assign to that object might not have had that property that you assigned it to before. Like a key, so I could assign like a key to something, right? That object might not have had that something before. To like assign an object a key, but that object might not have had that key before. That's what they're saying. A key, an application assigned to an object is not necessarily unique. So yeah, you could, whatever you assign to an object is not unique. An application may even change an element's key if it needs to. Yeah, so you could change an element's key. For example, you could compare companies by earnings or by number of employees. Hence, either of their parameters can be used as keys. Yes, depending on the information we wish to extract. Likewise, we can compare restaurants by critics' food quality, rating, or by average entree price. Yes, okay. To achieve the most generality, then we could allow a key to be of any type that is appropriate for a particular application. Yeah, so keys don't have to be unique. They don't have to be like completely unique, right? It could be like the price of this object. Well, that price is it's not a unique thing, right? You can have another object that has another price, right? So it doesn't have to be unique. That's what they mean. In the examples of the key used more often is a single numeric value such as a price, a length, a weight, or speed. That is, a key can sometimes be more complex property that cannot be qualified or quantified with a single number. For example, the priority of a standby passenger is usually determined by taking into account a host of different factors, like frequent flyer status, fare paid, check-in time. So yeah, in some applications, priorities can be very complex. They don't have to be like just a price or whatever. So some applications, the key might be data abstracted from the object itself. So it could be a member variable storing the price of a book, and you could use that as a key for a certain object. In other applications, the key is not a part of the object, but is externally generated by the application. For example, a quality rating given to a stock by a financial analyst, or a priority assigned to a standby. Okay, yeah. So they're basically saying that keys don't have to be explicitly unique. They could be also be very complicated, like complex, for whatever reason, and they could be a certain attribute for the object itself. So you could assign, let's say an object had a color, right? Let's say you want to order a bunch of headphones by priority, right? Well, each headphone had like a member for the color, a string of the color, right? So then you could be like, okay, well, I'll map a key for whatever color it is, like the color to whatever headphone it is. That's what they mean by that. So it can't be, it doesn't have to be explicitly generated by the application, whatever. You can compare keys with total orders. Priority queue needs a comparison rule that never contradicts itself. In order for comparison rule, you denote the not less than or equal to, and it must define in total order relation, which is to say that the comparison rule is defined for every pair of keys, and it must satisfy the following properties. Okay, reflexive property, k is less than or equal to k. Antisymmetric property, if k1 is less than or equal to k2 and k2 is less than or equal to k1, then k1 is equal to k2. Yeah. I guess so, yeah, that's a property. Okay, transitive property, if k1 is less than or equal to k2 and k2 is less than or equal to k3, then k1 is less than k3. Okay, yeah, these make sense. These make sense because of the less than or equals to sign, like when you compare anything. Okay, so it never leads to contradiction. In fact, it might define a linear ordering for a set of keys. If a finite collection of keys has a total order for it, then the notion of the smallest key, k-min, is well defined as a key, such that k-min is less than or equal to k for any other key k in our collection. They're just saying if you order something, you might, if you order the collection of keys, you might have a minimum key, and the minimum key is always less than or equal to the whatever key you're defined in the current set, whatever key is in your collection. So if you have like a set of keys, well, they're just defined, the minimum one has to be less than or equal to the other ones. Priority queue is a container of elements each associated with a key. The name priority queue comes from the fact that the key determines the priority used to pick the numbers elements to be removed. The fundamental properties of a priority queue are as follows. Insert the element E into P. Return the minimum. Min returns an element of P with the smallest key value. Okay. Remove or minimum. Remove from P this element min. Okay. Note that more than one element can have the same key, which is why we were careful to define remove min to remove not just any minimum element, but the same element returned by min. Some people refer to remove min as extract min. Are they saying the... Okay. Thing is, you could have two minimum values though, right? So It removes the same element returned by min. Okay, so I'm guessing, does it return? So if you have two of the same elements, does it return both of them? They didn't explicitly state that. Suppose a certain flight is fully booked an hour. Okay, so this is an example. Departure, because of the possibility of cancellations, they need a priority of the standby passengers hoping to get a seat. The priority is determined by the fare pay, the frequent flyer status, and the time. Passenger requests to fly standby. The associated passenger object is inserted into priority queue with insertion shortly before the flight departure if seats become available. The airline repeatedly removes a standby passenger with first priority from the first priority queue. Okay, so yeah. They're just saying that, okay, if there's like a problem with booking in a seat, not for an airplane to get your seat, right? You remove the ones with the first priority. That's what they're saying. Okay, let's talk about comparators. And one of the main problem in a priority queue is that you have to specify the total order relationship for comparing the keys associated with each element, and there are a number of ways to do this, each having its disadvantages. The most direct way is to implement a different priority queue based on an element type and the manner of comparing it. Okay, so they're saying that you could have so a different priority queue might have a different element type and a different way of comparing them. So they're saying like a different priority queue might have like a greater than or equal sign instead of comparing it by less than or equal sign, I guess. So like that way it'll arrange whoever is greater than, paid the most probably in an airplane, would go first instead of who paid the least. I don't know. While this approach is simple, it is not really that general, since it will require that we make copies essentially of the same code, maintaining each multiple copies of the equivalent code, which is messy and error prone. Okay. Better way to design the priority queue is as a template class. Ooh, okay, another templates, where the element type is specified by an abstract template argument, say E. We assume that each concrete class that could serve as an element of our priority queue provides a means of comparing two objects of type E. This could be done in many ways. Perhaps we require that each object of type E provides a function called comp that compares two objects of type E and determines which is larger. Perhaps we require that the programmer defines a function that overloads the lesson. Okay, so they're saying that they're going to overload the lesson operator in order to compare the whatever two objects of type E. And that basically, when you create your priority queue, it'll tell you who has the more priority based on your two objects. This is called a function. So they have a class called point2D that defines a point. It has an x and y value, like an x coordinate, y coordinate. So if they have the same x coordinate, return if the y coordinate, whoever has a. Okay, if they have the same x coordinate, then return whoever has this, return whether the first has a smaller y coordinate than the second. Otherwise, just return whoever has the smallest x coordinate if the first has a smaller x coordinate. Okay. This approach of overloading this is general enough for many situations. Some of okay, so they're just saying that is good. It's a good way of comparing, okay? Because if you overload the lesson, you tell who has more priority between two objects. There are at least two ways of comparing the strings. Okay. So here they just said whoever has, okay. Basically, they overloaded the lesson signs so say that who's going to have the more priority. Well, if they both have the same x value, they're going to return whether or not the y values are greater or whatever, right? And if otherwise, they'll return the x value if the first x value is less than the second. Okay, then so if it returns false, I'm guessing the second one has more priority. That's what I'm guessing, right? Because they're comparing the first y value and the second one and see if if this is less than that for their y value. So that means that if it is, I'm guessing this would have more priority because it's greater than, right? I guess it define depends on how you define it. They didn't give us any details. There are ways if we determine these. Okay. So there are two ways of comparing the C++ strings. You could have 4 is greater than the string. You could alphabetize the string so that 4 is greater than 12 because of alphabetical order. But you could also interpret them as integers. 4 is less than 12. Okay. Geometric algorithm occurs when 2 points in time P is less than Q if P of X is less than Q. Sort them left to right while another algorithm may compare them by Y coordinate. Sort them from top to bottom. Okay. There's nothing pertaining to the concept of a point that says whether points should be compared by X or Y coordinates. There are many other ways to define them. Okay. There are a couple of ways to achieve the goal of independence of each element type in comparison method. The most general is called composition method. Is based on defining each entry for our priority queue to be a pair, E element and a key. This element stores the data and the key stores the information for the priority ordering. Each object has its own comparing function. This is very simple. Okay, so they're basically saying you could write a method just like the operator overloading. They overload lesson, right, to see who has priority. Well, they're just saying here that you can maintain the priority based on the keys, the ordering using the lesson operator, right? Who has more priority, and then order it by the element and whoever has the highest key, right? That's what they're saying here. And you could change it anytime the order. Okay. The approach you use is a bit simpler than the composition method. It is using a comparator whose job is to provide various definitions of comparison function between any two objects. This can be done in various ways. In C++, a comparator can be implemented as a class that defines a single function whose job is to compare two objects of the same type. Okay, so they're gonna have a comparator function that overloads the parentheses operator, and this would just return true if A is less than B for comparing two objects. I don't know why they're doing this, because can't you, the other time they said they were going to overload the less than sign, but now it's like, okay, we're going to use comparator. It might seem at first that defining just a less than function is rather limited, but note that it is possible to derive all the other relationship operators without combining less than comparison with other Boolean operators. For example, we could test whether A is B with the less. Okay. Defining and using comparator objects. Let's consider a more concrete version of a comparator class as shown above. Let's assume that we have defined a class structure called point2D for storing a 2D point. Present two comparators. The comparator left implements the left to right order by comparing the x coordinates. The comparator bottom top implements right bottom to top by comparing the y coordinates. Okay. Let's call it left bottom top. Okay, left right. Okay, so here they have a comparator that compares left to right, which is who has the greatest left coordinate, x coordinate, and top bottom to top, which compares the y coordinate. These are the sole purpose comparison. Okay, so these are used to purposely specify a particular comparison operator given two objects P and Q. Test left, we would invoke the left. To test right, you invoke bottom top. Okay, yeah. Next, let us see how we use our comparators to implement two different behaviors. Consider the generic function print smaller. Takes two small objects. Okay. The comparator is assumed to be implement a less than function for two objects of type E. The function is given three arguments. The two elements P and Q to be compared, and an instance is less than of a comparator for these elements. The function invokes the comparator to parameters as well. Okay. So basically, this function just prints out which object is smaller based on the priority of the comparison operator. So the called is less than, right? And whoever's less than, it'll print out that. And is less than is basically just of comparing the it it's a class that it's a class that they made comparing the left and right, which is greater for the x and y coordinate, I guess. Well, I don't see where is it less. Finally, the code. Okay. Then to declare two comparator objects, one for left and right, top ordering. Finally, we invoke the function print smaller on 2 points, changing only the comparator objects in each case. Observe that depending on which comparator is provided. Okay, so they pass in a comparator, which is this, and to compare, which is the class that they had, is less. And the class, basically, you could pass in whatever the overloaded operator for who has more priority. That's what they're saying. So here that you could pass in the left and right to compare the left or right objects, to compare the x coordinate, and you could also pass in the bottom to top. So that would order the 2D objects by either who the left the x coordinates. They'll order them by x coordinates or they'll order them by y coordinates. That's what they're saying. If you invoke the left to right ordering, it will compare them and order them by left to right. If you do bottom to top, you'll compare them. Whoever the most priority will be it'll order them by the y coordinates. Finally, we invoke the function print smaller on these two passing in, depending on what the comparator is called. Okay, so here they have left to right, bottom to bottom top, and then they pass in the class for these two, left, right, bottom, top. In this way, we have turned the desired result to different behaviors for the same two-dimensional point class. Through the use of comparators, a programmer can write a general priority queue implementation that works correctly with a wide range of contexts. In particular, the priority queues present in this chapter are generic classes that are implemented by templated by 2 types, E and comparator. Comparator is a bit less general than the composition method because the comparator bases decisions on the contents of elements themselves. If the composition method, the key may contain information that is not part of the element object. The comparator approach has the advantage of being simpler since we insert elements directly into priority queue without creating element key pairs. Okay, so basically, this is just explaining how if you use the comparator approach by passing in the comparator, you're not basing it off of key pairs, like what we had talked about before, of having a key, and then a key, and then an object for each key, right? Instead, if you use the comparator approach instead of the composition method, you have the advantage of using it's not as general. It bases decisions on the contents of the elements themselves. So, as opposed in the composition method, the key may contain information that is not part of the element object. The comparator approach has the advantage of being simpler, and you could insert the elements directly into a queue. So it's just a simpler way of doing it. That's what we're saying, without creating element key pairs. So let's talk about priority queue ADTs now. So, having described the priority queue abstract data type as an intuitive level, we can now describe it in a more detailed level. As an abstract data type, a priority queue supports the functions. You could return the elements array, you could check if it's empty, you could insert a new element, you return the minimum element with the smallest key value, which this is good, this is really good. Remove minimum, this removes a minimum. Error occurs if it's empty. As mentioned above, the primary functions of the priority queue are the insert, minimum, and remove minimum operations. The other functions, size and empty, are general collection operations. So size and empty, this occurs for anything actually. These are just general functions. No, we could apply a priority queue to have multiple entries with the same key. So here they show a table, a series of their operations and effects with an initially empty priority queue. Each element consists of an integer, which we assume to sort it in the natural order of the integers. Note that we call minimum to return a minimum reference. Okay, so they're basing the priority based on the they're basing priority based on how the largest, whoever has the largest value, right? So Here you insert 5, then you insert 9, then you insert 2, and then you insert 7. It's ordered by smallest to largest, and if you remove min, you remove the smallest value currently, which is 2. Here 2, and then you get size. You remove min again, it removes 5. You have 7, 9. You remove min, you get an error. If you after you remove min a bunch of times, you get an error. Okay, a C++ priority queue interface. Before discussing specific implementations of the priority queue, we first define an informal C++ interface for a priority queue. It's not a concrete class, it's just about public functions. Okay, so these are all the same functions we had before. Although the comparator type C is included as a template argument, it does not appear in the public interface. Okay, so this is a template argument, the comparator. Of course, its value is relevant to only concrete implementation. Otherwise, the function min returns a const reference to the element for the priority, which means that its element may be read and copied but not modified. Okay, so that is important because otherwise the user might not modify the element's key. Okay, so they're just saying here that it's important that they made a const because they don't want to modify the key value. This could corrupt the whole data structure because you're basing it on the priority for the key. An error occurs if either of these functions, min or min remove, is called on empty queue. Yeah. Okay. So let's talk about sorting with the priority queue. Another important application of a priority queue is sorting, because we are given a collection of n elements and you want to reorder them, rearrange them in increasing order, at least increasing order or decreasing, it doesn't matter. An algorithm for sorting L with a priority queue is called priority queue sort. It is simple because it's the following 2 phases. First phase, we put the elements L into an initially empty priority queue, P through a series of n insert operations, 1 for each element. In the second phase, we extract the elements from P in non-decreasing order by means of the series of n combinations of min and remove operations, putting them back into L in order. Okay. So here's how they're sorting it. So given a list of numbers, it compares them while it's not empty. We take the front and remove element E from the list. And then you insert it into the priority queue. Okay. Then while it's not empty, you get the minimum, remove it, and you add it back to the list. So this is basically just saying that they're basically just going to remove all the elements from a list of like the vector or whatever, list or whatever, and they're going to add it to a priority queue. Then they're going to remove the minimum and then add it back. So that's going to sort it because the priority queue is already sorted based on the minimum value. So if you insert your value into the priority queue, it automatically sorts it by itself based on the minimum value. And then you could just loop through the whole priority queue, remove every single minimum value, and then add it back to the list, vector or list or whatever it is. That's all they're doing here. This is not really a good way to sort, I think, because they're assuming that, well, I just don't think this is a good way. It's not really a sort algorithm. It only works for a priority queue P no matter how P is implemented. However, the running time is determined by the running times operation insert, min, and removement. Yeah, which do depend on how P is implemented. Indeed, priority queue should be considered more a sorting scheme than a sorting algorithm because it does not specify how the priority queue is implemented. The priority queue sort scheme is a paradigm of heavy costs of popular algorithms. Yeah, so it's not really an algorithm. All right, let's talk about the STL Priority Queue class. So the STL provides implementation of a priority queue called Priority Queue. So now we're going to talk about the real priority queue, like the one that STL has, the one that C++ has, right? The standard template library. As with other STL classes we have seen, such as stacks and queues, is an example of a container, priority queue. In order to declare an object of a priority queue, it's necessary to first include the definition file called queue. as with othering, and include the using statement. Okay. Is template with 3 parameters, the base type of elements underlining STL container in which the priority queue is sorted, and the comparator object. Only the first template argument is required. The second parameter defaults to the STL vector, and the third parameter defaults to using the standard SC++ lesson operator. Okay, so they're just saying that so the STL, the priority queue class, has 3 parameters, right? First of them is just the type of object you're creating. So if you want to create a priority queue of integers, queues, whatever object, in this case it's point, 2D, whatever it is, right? This is required, right? These 2 are optional, right? If you don't include them, for the middle one, they're just going to assume that it's the STL vector, which is the vector that we had, which is like an array, like an array, right? Except you could resize it. They're just going to assume it's a vector. If you don't include this part, left, right, they're just going to use the standard lesson operator. And if you didn't override the left-hand lesson operator, I don't know what would happen for your object, because there's no comparison. They don't know who has more priority than another. So the priority queue is compared to the same manner as the one. You have to. Comparator is a class that overrides the parentheses operator in order to find the Boolean function that implements the lesson operator. Principal member functions of the STL priority queue are given below. Let P be declared to be a STL priority queue, and let E denote a single object whose type is the same as the base type of a priority queue. P is a priority queue of integers. E is a what was it? Integer. Okay. So you have size, empty, push, top, pop. Top removes the largest element of the priority queue. Oh, so it's the largest element now. Okay. Removes the element at the top of the priority queue. Okay. Other than the difference in function names, most significant difference is the top and pop. It acts as the largest element according to priority order rather than the smallest. Okay, so what's different about the standard library, standard STL, is that it uses the top and pop rather than the largest rather than the smallest. Of course, it's possible to simulate. Okay, so here they add, they created a vector of priority queues, right? They have a priority queue, right? And they're gonna use of type object, which is the type of point 2D. It's going to, second parameter is gonna be they're going to use a vector for the second parameter, and then the third parameter they're using the comparator left, right. And basically what I mean by the second parameter is the second parameter is underlying the default. I'm guessing it's just like the way you're going to store the second parameter. They didn't specify it. Okay. Oh, okay. So the second parameter is the underlying STL container in which the priority queue is stored. Okay. So the way that they're storing this is using a vector to store the values for each priority, right? And then they're using the object to point 2D, and then left, right based on the comparator. So then they add p2.push. So this is going to be a priority queue of a vector. So then you could use a push, and then you add these objects to it, and you get the top, and it returns the largest one. Of course, it is possible to simulate the same behavior by defining the comparator object so that it implements the greater than relationship rather than less than. This reverses all the order, and thus the top would be the smallest. Yeah. Note C plus STL priority queue does not perform any error checking. Alright, now we're going to talk about implementing a priority queue with a list, which is different than what we were using before. So here, they're gonna try to implement a priority queue with a list. So they're gonna consider an unsorted doubly linked list, and they're gonna try to basically perform the operation insert by adding a new element to it by doing pushback, and this insertion takes O of 1 time. And then because it doesn't result in a key value, like consider key values, the list is unsorted, right? As a consequence, in order to perform either the operations min and remove, you have to go through every single one of them to find the minimum key. Thus, min and remove would take over n time each, where n is the number of elements. And moreover, each of them run in time proportional n to the best case, since they are searching through them to find the smallest element. So you could say that they run in, I think it's theta of n. Yeah. If you implement size and empty by returning the output of the actually you get like if you implement the function size and empty by simply returning the output of the corresponding functions execute on the list. By using an unsorted list to implement a priority queue, you achieve a constant time insertion, but linear time search and removal. That's what they're saying. You could do implementation with a sorted list, which is better. Basically, they're just this time they're going to store them by their key values. Specifically, you represent the priority key by using a list L elements sorted by non-decreasing key values, which means that the first element of L has the smallest key. Okay, so if you go through the whole list, the first element of L has the smallest key. You can implement the function min by accessing the element associated with the first element of the list with the begin function of L. And you can implement remove list by using pop front. Assuming that L is implemented as a doubly linked list, operation min and remove take O of 1. The problem of that is that you have to scan through L to find the appropriate position it takes to insert the new entry. Thus, implementing insert now takes O of n, where n is the number of entries. So basically, when using a sorted list to implement priority queue, insertion runs in linear time, but removing is constant time. Here's a table that basically just contrasts it by using a sorted list or unsorted list. Yeah. So here's the C++ priority queue implementation using a list. You can present a priority queue implementation that stores the elements in a sorted list. The list is implemented using an STL list object, but any implementation of a list would suffice. You present the class definition of our priority queue. The public part of the class is essentially the same as the interface that was presented earlier in code fragment 8.4. In order to keep the code as simple as possible, we have emit error checking. Classes data elements consist of a list which holds the priority queue's contents and an instance of the comparator object. Okay, is less. Okay. They don't bother giving explicit constructor. Okay, so this is basically they have their own list, priority queue contents, and they have a lesson comparator here. And they have all the methods that we talked about before, and then this is the class list priority queue. Oh, they're gonna. Okay, so they didn't give a constructor. What is this? Okay, so the size and whatever empty, they just called L.size, L.empty. So how are they gonna insert an element? Well, they're gonna create an iterator, and it's gonna walk through the list until they find the element whose key is larger than it. Then they're gonna insert the element just before it. So recall that star p accesses the element referenced by p, and plus p advances p to the next element of the list. So p is an iterator, by the way. You stop the search either when you reach the end of the list or when you first encounter a large element. That is one satisfying is less. On reaching an entry, they insert e just prior of it by invoking the insert STL list. So they're going to go through the whole list, and while it's less than it, Oh, well, it's not less than a plus plus. And then they insert it at that position. They call the insert function from the list class, right? What was they use? They used the list, I think, right here. List E, list L, yeah. Consider how the function behaves as E has a key larger than anything. In this case, a while loop exits. Yeah, okay. L dot n refers to an imaginary element that lies just beyond the end of the list. By inserting before this element, we effectively append E back to the list. Okay. You might notice the year type name. Okay, so the reason why they have the keyword type name is because of the problem with dependent names, which happens when processing name bindings with templated objects. You do not simply delve into they didn't delve into the problems of this, but for now it suffices to remember to simply include the word type name in this case. Okay. Finally, they consider min and remove. Since the list is sorted by ascending order by key values, in order to implement min, we simply return a reference to the front of the list. And we remove the front of the element of the list. Okay, so they use pop, and then they use return front. Okay. You guys might be wondering how it's sorted in order now. Well, it's because the insert operator goes through it and checks whatever it's less than it would, and then it inserts it before, right? So then this whole thing is going to be in order because they're inserting it based on is less than. So they're going to, so let's say if I have like 8, okay, wait. Let's say I have the number 8 first. And then I want to insert, okay, let's say I have 5, 8. I want to insert 10. Well, it's going to loop through here, and then it checks while it's less than it, and then it's going to add 10. Because it's less than 5 is less than 10, 8 is less than 10, so it's going to add 10 here. Now, let's say I want to insert 6. Well, it loops through it. Is 5 less than 6? Yes. Then they're going to check 8 is not less than 6, so then they're going to insert it prior to it. Right? That's what they're doing. They're going to keep going right until they basically keep going right until they find whatever that's greater than it and then insert it. So that's why it's always in order. It's technically not sorting because the list is in order. Yeah. To remove, they just call the function pop front, which is this is a function this is a function in the STL vector class. This is kind of cheating because they're calling another function to remove the front. They remove the minimum. Whatever. Like they're calling a function that is already implemented. Like what's the point of implementing a priority queue then if you're just gonna call their remove like front? Why not just use their priority queue? Okay, so now we're gonna talk about selection sort and insertion sort. We already went over this, I think, but I mean, like I think we went over that in like way back, but I don't remember. Recall that okay, let's say you want to sort something, right? Selection sort. If you implement it with an unsorted list, then the first phase of a priority queue takes O of n time, since you have to insert each element in constant time. The second phase of min and remove is proportional to the number of elements current to P. Thus, the bottleneck computation is an implementation in the repeated selection of the minimum element from an unsorted list. For this reason, this is known as selection sort. So, what are they doing? They're basically just... Okay, so if you use a not unsorted list for a priority queue to implement it, you're basically using selection sort because you're basically going to loop through it. You repeatedly loop through it, get the smallest element from the priority queue, and then put it in the front. So here they... Wait, let me see. What are they doing? It took the smallest element 2, and Yeah, I'm guessing that's what they're doing. So they took 2. Okay, so this is their list. They removed 7. Well, this isn't really selection sort. They're not really doing. I'm pretty sure selection sort is like you find the smallest one and you put it into the front. I'm 100% sure that that's what it is. Okay, so yeah, it finds the smallest elements in the unsorted list and swaps it with the leftmost unsorted element, and then moves to the right. Okay, yeah, so that's basically what they're doing. They're finding the smallest element, which I don't know why they're not showing it here. Why? So find the smallest element 2 and then swap it with 7. That's what they should show, but they're not, which is weird. Oh yeah, this is the math behind it, and you have n times n plus 1 over 2. It takes over n squared. This doesn't matter currently. Okay, so another thing is insertion sort. If you implement a priority queue using a sorted list, you improve the running time by O of n because each operation takes O of 1. Unfortunately, the first phase now becomes bottleneck for the runtime. It takes proportional to the size of P. This sorting is better known as insertion sort. Okay, so I think we already went over this. You just take the element and insert it between it. I don't understand what their diagram is doing here. They took 7 out, then where did they put it? Oh, okay, they put 7 in this priority, right? Then they take 4 out, put it in here. Then they take 2 out. No, they don't take 2 out. They take 8 out, and then they add it at the back of 8, and then they take 5 out. They don't take 5 out. They take 2 out, add it at the back. Yeah, and they just keep going. Take 3 out, they take 9 out, just keep at it. Yeah, until it's empty. And now they have the priority queue for the list. And they're gonna remove the smallest one, adds it to the priority queue. So this is the math behind it. It runs n square. Also, you could change your definition insertion sort so that you insert elements starting at the end of the priority queue in the first place, in which case the insertion sort is priority sort would run O of n instead. Indeed, the running time of the insertion sort is O of n plus I. In this case, I is the number of inversions on the input list. Number of pairs of elements that are going wrong in a wrong relative order. Okay. All right, now we're going to talk about heaps. So basically, what is a heap? A heap is basically a binary tree that stores a collection of elements with their associated keys at its nodes, and it specifies 2 additional properties. A relational property in which the keys are stored in T, and a structural property in terms of the nodes itself. So we assume that the total order relation of the keys is given by a comparator. And what is the good thing about a heap? Well, the good thing about a heap is that it's better. It allows you to have insertion and removal in logarithmic time to remove the smallest one or the largest one, compared to what we had before, which is the priority queue sort. That's a good thing about a heap. So let's just talk about what do they mean by this? Well, they're basically saying, when they're talking about the relational properties, they're saying that it's let me see, they found a way to use it. Okay, they're saying that the keys are sorted in order, and a structural property, that's just saying the nodes are, I'm guessing they're in order. I don't know, but in a heap, for every node V other than the root, the key associated with V is greater than or equal than the key associated with the parent. So the key associated with the the node is always greater than the parent for every node other than the root. Okay. As a consequence of the heap order property, the keys encounter on a path from the root of an external node of T are in non-decreasing order. Also, minimum key is always stored at the root of T. This is the most important key and is informally said to be at the top of the heap, hence the heap for the data structure. So the minimum key is stored at the top of the root, and the keys are encountered on a path from the root to an external node are in non-decreasing order. Okay, so the minimum key is stored at the top. That's why it's called a heap. You might wonder why heaps are defined with the smallest key at the top rather than large. Distinction is arbitrary. So it could be the largest, the opposite. So here we have a key for element 4. Let's see, 5A, 15K, 9F. Here's an example of a heap storing 13 elements. Each element is a key value of the form K and V. The heap is ordered based on the key value K of each element. So the heap is ordered based on K, and the K is the number. So it's ordered based on number. So Z is bigger than C. Wait. No, that doesn't make sense. Yeah. It's ordered based on the number. 6 is greater than 4. 20 is greater than 6. 7 is greater than 6. 5 is greater than 4. 15 is greater than 5. 9 is greater than 5. 16 is greater than 15. 25 is greater than 15. 14 is greater than 9. 12 is greater than 9. So all these are 11 is greater than 9. 8 is greater than 9. 20 is greater than 6. So yeah, the heap is ordered based on the key. In this case, it's K. The K is the number. C is the value. The letters are the value. V. Suppose we have instead based our comparator to indicate the opposite of the sorted total order relationship between the keys. That is less than would return true if X is greater than the root of the key, which is the largest key. Yeah. So if you done is instead of is less, you do is greater than, the root would be store the largest key. By defining the minimum key in terms of compare the minimum key with the reverse operator is the greatest, thus without loss of generality, we assume that we are always at the minimum key, which is always at the top. Okay. For the sake of efficiency, which becomes clear, we want the heap T to be to have as small of a height as possible. We enforce this desire by insisting that the heap T satisfies an additional structure property. It must be complete. Before we define the structural property, we need some definitions. We recall from the section 7.33 that level I of a binary tree is a set of nodes of T which have a depth of I. Given the nodes V and W on the same level of T, we say that V is to the left of W. If V is encountered before W in order traversal, and there's a node between the left and right. For example, the binary tree storing the tree 15K is at the left side storing 7Q. So we're going to talk about this property now. The to the left relationship. Complete binary tree property. A heap T with height H is a complete binary tree. That is levels 0, 1, 2 up to H minus 1 of T have the maximum number of nodes, namely I has to the I nodes for I is less than or equal is greater than or equal to 0 and less than or equal to H minus 1. And the nodes at level H fill this level from left to right. So what does this mean? This is basically saying that if you want to have a heap, it has to be complete. So before you add nodes on the next level, the previous level has to be fully, like completely filled. That's what they're saying. So I can't add this node on this side until this is done. Right? I can't have a node. All they're saying for a heaped complete binary tree, they're just saying that, like, if I have a node, let's say for, I'm not going to say the values. I'll just order the keys, right? 6, 15, 9. Okay. 7, 20. What was it? Okay. So it's basically saying that if I want to add a number here, I cannot add it right here. You cannot do this. Okay, you cannot add it. When you add nodes to it, it has to be complete. So that means that before you add on to another level, the node has to be complete. So this has to be added here on the left before you could add another node here. That's all they're saying. That's what it means by complete. I don't know why they making so much complicated language of that, but that's all they're saying. Like it, you cannot have a heap like this, right? This is not, you can't have this because this 15 should be over here. This 15 should actually be over here if I rotate it correctly. I can't rotate it. Whatever. So this 15, this is not complete. Why? Because before you finish this level, before you add a node onto the next level, you have to finish it. So this 15 should be over here. You have to finish the level. Not only that, is this a complete binary tree? No, it isn't, because everything has to be, you have to finish the level, as in that you can't have an empty space here, right? You can't have an empty parking lot, or you could imagine this as a parking lot. Sometimes in a parking lot, when you park a car, you don't want to be parked in completely empty spaces. Like sometimes they don't allow you to park in like a random empty space. It has to be right next to the other car that's already parked. So that's why you can't have this. This is not a complete binary tree. It has to be complete. That means it has to be right here. It has to be over here. Before I add nodes on this side, I have to finish this node on this side first. And before I add nodes like that, I can't add nodes like this, right? I can't have a node like this. I have to have, there's an empty space here. I have to make sure all the spaces are filled before I add another node. That's all what they mean by a complete tree. So that's basically what separates a heap. And also in a heap, the smallest key or largest key is on the top. So this is the smallest heap, smallest key. So that's basically what a heap is. Smallest keys on the top. And complete. Just making sure you guys understand. It must define the level left to right. Okay, yeah. Let h denote the height of t. Another way of defining the last node of t is that it is a node on level h such that all other nodes of h are to the left of it. Yeah, so that's what I'm saying. All the nodes have to be to the left of it. Here's just a justification. I don't know why we're doing this. It implies that we perform update operations on the heap. Of course, we know the operations will align on algorithms. Okay, so yeah. This is just doing inequalities using some math on it. It doesn't matter. Alright, so let's talk about complete binary trees and their representation. So we already talked about this, right? You have to be complete before you add another node, alright? And then I'll talk about this after I get it. Alright guys, we're going to talk about complete binary trees and their representations. So as an abstract data type, a complete binary tree supports all the functions of the binary tree, plus the following functions. Add to t, returns a new external node v, storing element e, such that the resulting tree is a complete binary tree with the last node v. Remove removes the last node of t and returns its element. So by using these update operations, the resulting tree is guaranteed to be a complete tree. And there are essentially two cases for the effective add, and the remove is similar. If the bottom level tree is not full, then add inserts a new node to the bottom level of t immediately after the rightmost node. So like this, inserts w, right? That is the last node, hence the height remains the same. If the bottom level is full, then add inserts a new node on the left child of the leftmost node. So insert like that. So this is already full, insert one on the height, and height increases by 1. Example of these add and remove on a complete binary tree where w denotes the node inserted by add and deleted by remove. The trees shown in B and D are the results of performing add operations on the trees in A and C, respectively. Likewise, the trees shown in A and C are the results of performing remove operations on the tree B and D, respectively. Alright, so you have a vector representation of a complete binary tree. Vector representation is specifically suited for a complete binary tree. We recall that this implementation, the nodes of T are stored in a vector A such that the node V in T is the element of A with index equal to the level number f of V. So what does that mean? So so the nodes of whatever tree are stored in a vector such that whatever node in the vector in whatever node in the tree is an element of the vector with an index equal to the level number. That's what they're saying. Okay, so the node of the tree holds a vector that basically has no. The node doesn't hold a tree. Okay, there's a vector for every node in this tree. The vector stores it based on the index number from the level number. So whatever level this is, that's what they're saying. Okay, I just broke it down to you. Okay. So whatever node, the nodes stored in T are stored in a vector, and the vector, basically, the index is basically whatever level number is. Okay, so if V is a root of the T tree, then the level number starts at 1, so it's 1. If V is the left child of a node U, then the level number is 2 times the f of U, and f of U is the 2 times the what is U? Wait, I'm guessing it's just a function for the index. Yeah, and then if V is the rightmost of the right child of U, then f of U is fv is equal to 2 fu plus 1. So with this implementation, T has continuous indices in the range 1 to n, with the last node of T is R is at the index n. So yeah, so they're basically saying they're storing each node at a specific index, right? And it's based on the level number. So they didn't have an example, but 2 examples show the last node n nodes has level number n, a heap T1 with more than 1 node on the bottom level, and B heap T2 with 1 node on the bottom level. Vector-based representation. Okay. The simplifications from representing a binary tree with a vector aid in the implementation of the functions add and remove. Assuming that no array expansion is necessary, functions add and remove can be performed in O of 1 time because they simply involve adding or removing the last element of the vector. Moreover, the vector associated with T has n plus 1 elements. The element at index 0 is a placeholder. If we use an extendable array that grows and shrinks for the implementation of the vector, the space used by the vector-based representation of a complete binary tree with n nodes is O of n, and the operations add and remove take O of 1. So here's the interface that has all these methods. They have an interface of a nested class called the position that represents the node of the tree, and they provide functions to access the root and the last elements to navigate through the tree. So we have the position, we have left, right, parent, has left, has right, is root, last, add last, remove last, swap. In order to implement this interface, we store the elements in the vector that we called before. They implement a tree position as an iterator to this vector. To convert from index representation of a node in this positional representation, we provide a function pos. The reverse conversion is provided by function idx. This portion of the class definition is given in code fragment 8.19.112. So yeah, begin plus 1. Okay, so this is just a position. This maps an index to the position, and this maps a position to an index. Okay, idx, and it returns the index of whatever position it is. This returns the returns the index to whatever, returns position to whatever index, I guess. Yeah. Okay. Let's go to the next class. So given the index of node I, the function pos maps it to a position by adding it to the beginning of the vector, and you could exploit the fact that STL supports a random access iterator that, in particular, if we're given an integer I, the expression v begin plus I yields the position of the ith element of vector, and given a position p, the expression p minus v dot begin yields the index of the position p. We represent a full representation of vector base here, right here. Okay, so yeah, they're just saying the position. Okay, so these are all the functions that we had last time. Recall that the root node is at index 1 of the vector. Yeah, we know that. Since STL starts at 0, our constructor creates an initial vector with 1 element. Yeah. So here they created initial element with 1 element. This element is indexed at 0 is never used. As a consequence, the size is 1 less than the size of the vector. Okay, yeah. Recall that given a node I, its left and right children are located at indices 2i and 2i plus 1 respectively. Its parent is located at index I over 2. Given a position p, the functions left, right, and parent first convert p to an index using the utility index, and then it does appropriate arithmetic on this index and finally convert the index back to position. To determine the child by evaluate the indexes, tested whether the node actually exists at the vector. Okay, so positions add in, remove by implement by add and remove last entry. Okay, so let's talk about implementing a priority queue with a heap. So now that we talked about how to implement, now we discussed how to implement the priority queue using a heap. Our heap-based representation consists of the following. So we have a heap, a complete binary tree that stores the elements of a queue and whose keys satisfy the heap order property. We assume that the binary tree T is implemented using a vector, as described in this section. For each node V of T, we denote associated key by K of V. Comp, a comparator that defines the total order relationship among the keys. So here's the comparator, and then here's the heap. Okay, with this data structure, the size and empty takes 1, O of 1. Yeah, that makes sense. In addition, the function min can be easily performed in O of 1 time by accessing the entry stored at the root of the heap. Okay, so let's consider how to insert into a priority queue implemented. To insert a new, you just add a new node to it with the operation add. Then this new node becomes the last node of T. Then you store E into this node. Then store E into this. Okay, so after this action, the tree is complete, but it may violate the heap order property. Hence, unless node Z is the root of T, we compare the keys and then store out the parent of Z. So if the keys are greater, then the heap order property is satisfied and the algorithm terminates. If instead KZ is, if the keys are less, then you swap it. This swaps the new entry to move up one level. So here, they add a new thing, 2t, right? Because 2t is less than 20b, and you want to satisfy the property, the heap order property, which basically, the heap order property basically says that the keys have to be in order from like greatest to least, I think. So that's why they swap it. They swap these values together. Okay, let's go to the next one. So yeah, then they keep swapping it because the keys have to be less. The 2 has to be less than 6, right? So then they swap it again. Yeah, and then 2 is less than 4 now. 4 is less than 6. 6 is less than 20. Yeah. So now that fixes the heap order property. The movement is called up heap bubbling. That's cool. The swap resolves a violation of heap order property. Okay, yeah. And it's log of n. Alright, so now let's talk about removing the minimum value. We know that the element with the smallest keys is stored at the root of T. However, unless R is the only node of T, we cannot simply delete node R because this action would disrupt the binary tree. Instead, we access the last node of W and copy its element to the root and then delete the last root. Okay. Down heap bubbling after removal. We are not necessarily done, however, for even though T is now complete, T may now violate the property. If T has only one node, then the heap property is trivially satisfied and the algorithm terminates. Yeah. So otherwise, we distinguish two cases where R denotes the root of T. If R has no right child, let S be the left child. Otherwise, R has both children. And let S be a child of R with a smaller key. If the keys are less, then the algorithm terminates. If the key is greater than, then they need to restore the heap order property. So they swap the entries stored at R and S. The swap we perform stores the key order property for node R and its children, but it may violate the property at S. So you continue swapping it down until the heap property occurs. This is called down heap bubbling. A swap either occurs violates the heap property at one level down the heap. In the worst case, an entry removes all the way down to the bottom heap. Okay. So if you... Whoa. My bad. Okay, so it's right here. I think it was this one. So we're gonna look at this. Okay, so here they remove... Wait, what are they doing? Okay, so they're gonna remove this node, which was 13W. Oh, no, they're removing 4C, I think. Yeah. So they take the bottom node of the bottom right child and move it to the top, and then they keep swapping it to make it back in order. That's how they're removing it, to keep it in order. Yeah, and then whatever's smallest moves back to the top. Okay, so this performs a heap or property. It's O of 1, minim's O of 1, inserts over log of n. I guess it's log of n because you just swap it. It goes log of n times. Okay, it performs log of n over n. If T has T nodes, sort of reference to entry. Operates add and remove on T either has O of 1 time or O of log n. To height. Okay, thus if a heat is if heap T is implemented with a linked list, the space need is O of n. Okay, yeah. If we use a vector trace instead, then the space is proportional to n. Yes, we conclude that the data is very efficient. Yeah, it's more efficient. Indeed, an important consequence of the efficiency of the heap-based implementation is that it can speed up the priority queue, sorting to be much faster than the list-based insertion sort and selection sort algorithms. So, let's talk about C++ implementation. How are we going to implement this? Alright, so let's talk about C++ implementation. Here's a class definition. Here's the interface that has everything. Size, empty, insert, min, remove min. Now they have a vector complete tree called T. Alright, and then they have a comparator. A lesson comparator to compare the keys, right? And then here, yeah. Priority queue, here's a vector complete tree. Here's the priority queue for the, excuse me. For this, the type def type name vector complete tree here. Yeah. Here's the implementation for all these functions, the size, check if it's empty. Minimum is always the root. The minimum is always on the top. Yeah. Here's the implementation insert. So they add it to the last node and they get the position of the last one. And while T is not the root, which is while it's not in order, right? They're gonna get the position of it, and then they're basically gonna swap it. They're gonna swap with the bottom one if it's not in order. Yeah, and this swaps it, and then they set swaps V to U, and then swap it. That's what it's doing. Okay, let's talk about remove in min operation. If the tree has only one node, then we simply remove it. Otherwise, we swap the roots element with the last element of the tree, and remove the last element. We then apply down heap bubbling in the root, letting U denote the current node. This involves determining U's smaller child, which is stored in V. This child's key is smaller than U. We swap U with the contents of this child. So if it's one node, you remove the last node. Otherwise, this is here just to swap it. If that was right, and if it's less, then you set U to the right child. If it is less than the U, then you swap it. That's all they're saying. Otherwise, you break and you'll be done. Okay. Alright, let's talk about heap sort. Alright, so you observe that a priority queue with a heap has the advantage that all the functions in a priority queue ADT run in logarithm time or better. Hence, this realization is suitable for applications with fast running times and are soft for the priority queue functions. Therefore, let us consider the priority queue sorting scheme, and which uses a priority queue P to sort a list L. During a phase 1, the ith operation takes 1 plus logarithm of I. Hence, the heap has I entries after the operation is performed. Likewise, during phase 2, when you remove the min, it's 1 plus log n minus j plus 1, where I think n is the number of elements and j is just the the jth element that you're removing. Thus it takes O of n log n. When you use a heap to implement the priority queue, this sorting is called a heap sort, and its performance is summarized in the position. Heap sort sorts a list of n elements in n log n time, assuming 2 elements of L can be compared to O of 1 time. Let us stress that O of n log n running time of heap sort is considerably better than O of n squared of insertion sort and selection sort. and it's actually the best possible for any sorting algorithm. Implementing heap sort in place. So if the list L is to be sorted implemented by means of array, we can speed up a heap sort and reduce its space by requirement by a constant factor using a portion of the list L itself to store the heap, thus avoiding the use of external heap data structure. This performance is accomplished by modifying the algorithm as follows. So we're going to use a reverse iterator, which corresponds to a heap where the largest element is at the top. At any time during the execution of the algorithm, we use the left portion of the L and then up to a certain rank to store the elements in the heap. On the right portion from the rank to store the elements on list, right? Thus the first Li elements at the ranks, rank is just the index or where the key, whatever, to provide the vector representation of the heap. The element at the rank k is greater than or equal to the children at ranks 2k plus 1 and 2k plus 2. So in the first phase of the algorithm, we start with the empty heap and move the boundary between the heap and the list from left and right, one step at a time. We expand the heap by adding the element at rank and perform up heap bubbling. And the second phase of the algorithm, we start with the empty list and move the boundary between the heap and the list from left to right, one step at a time. At step I up to the n, we remove the maximum element from the heap and store it at n minus 1, n minus I. So the above variation of heap sort is said to be in place since we are using only a constant amount of space in addition to the list itself. Instead of transferring elements out of the list and back in, we simply rearrange them. So we illustrate the in-place sort here. In general, we say that a sorting algorithm takes place if it only uses a constant time memory, as well as sorting algorithms consider space efficient if it could be implemented in place. Okay, so we start with this vector, right? Elements. Okay, so we have 3 in here. We have 3, which is the big root here, right? What are we going to do? Alright, we take 7. We're going to add 7 here, okay? So 7 is now the root, okay? We'll add 2. We're going to add 2. So then 2 is here also. And then what are we going to do? We're going to add 1, the next element, yeah. And then we're going to add 4. Okay? So we're going to add 4 here. Where's E? Okay, so now that we add 4, wait, parts A, B, C, 3, where's E? Oh yeah, okay, so we add 4. 4 is greater than 3, right? So we swap them. Okay, so what we're trying to do is make the maximum at the top. That's what we're trying to do. Okay, so we add 4 here, right? 4 is greater than 3, so we swap these two. So now, so we add 4 here, right? And then 4 is greater than 3. So okay, so imagine I added another node here. 4. See right here. 3 added 4 here. 4 is the next number here, right? That's why we add it. And then now we swap it. 4 is now above 3. Okay, so then that makes it that like that. Now we're going to they remove the top of the heap, which is 7, and then they reordered it, and they add 7 to the back of this new heap, right? Alright, so they reordered it, so now it's 1, 3, 4, 2. Then they removed the top element, which is 4, and added it back here in reverse order, right? Adding it then into the front, my bad. So now it's 1, 3, 2. Remove the top, which is 3. The top node is 3, right? So now it's 2, 1, 3, 4, 7. Remove the top of 2, which is now going to be 1, 2, 3, 4, 7, and then 1's the last one in place, so then that'll be it. And that's basically how heap sort works. So you just keep putting it in a heap, and then you just keep removing the top element of it and placing it back into the array. That's all you're doing. Okay, so basically for a heap, remember they here in this case they want the maximum be way on the top. So always put the maximum on the top and then swap with the nodes if it's not. Alright, let's go to the next one. Alright, let's talk about bottom up heap construction. So the analysis of the heap sort algorithm shows that we can construct a heap storing n elements in n log n time by means of n successive insert operations, and then we could use that heap to extract the elements in order. However, if all the elements to be stored in the heap are given in advance, there is an alternative way of doing this. We call it bottom up construction that runs O of n. We describe this in the function by observing that it can be concluded as one of the constructors in a heap class. Instead of filling a heap using a series of n insert operators, operations. For simplicity, we describe this bottom-up heap construction assuming the number n of keys is an integer of type n equals 2h minus 1. Now, as a heap is a complete binary tree with every level being filled, so the heap has height h equals log n plus 1. View known recursively bottom up. Wow, they're making this way too complicated. In the first step, we construct n plus 1 over 2. In the second step, we n plus 1 over 4. N plus, okay. Here's the example. Okay, so we have all these. Okay, so we have all these nodes, right? Here's the bottom tree, right? They're going to swap them to the smallest one on the top this time, okay? So they're going to swap the smallest one on the top, okay? And then, no. Wait. What are they doing? What are they doing? Okay, so the first step, we construct n plus 1 over 2 elementary heaps. In the second step, we perform n plus 1 over 4 heaps, adding new entry root. Third step, n plus 1 over 8 heaps. In the generic ith step, we form n plus. Okay, they're not telling me what they're doing. Yeah, I don't know. I don't know what they're doing here. I'm just gonna guess what they're doing. Okay, so they have this. Okay, they're gonna swap the smallest one to be on the top. Okay, so now they have 9 here. Where did this 9 come from? I don't know where this 9 came from. Okay, then they're gonna swap it. Okay, so the smallest one's on the top, and they keep swapping. All right, and then what are they gonna do? Okay, so now they have it. Oh, okay, so bottom-up construction is basically you begin by constructing one entry heap at the bottom level, and then you can combine these heap into 3 entry heaps, and then 7 entry heaps, and then you can create the final heap. Okay, so basically this is just a way to creating a heap in the end. They're just slowly creating heaps, multiple heaps on the bottom, and then connecting them together. That's all they're doing. Here's a recursive algorithm. While the list is not empty, then return an empty. If the list is empty, return an empty heap. Otherwise, you add e to the front. E equals to l dot front. Remove the front. Split it into 2 lists of n minus 2 size. So now you have a bottom up heap. To create 2 bottom up heaps, create a binary tree. The root R storing E, left subtree T1, and right subtree T2. Perform a down heap bubbling from the root R of T. If necessary, return T. Although the algorithm has been expressed in terms of STLs, the construction could have been performed equally well with a vector. In each case, so the splitting of the vector is performed conceptually by defining 2 ranges of indices, one representing the front half of L1 and the other representing the back half of L2. At first glance, it may seem that there is no substantial difference between the algorithm and the incremental heap construction using the heap sort algorithm. One works by down heap bubbling, the other one uses up heap bubbling. It is surprised, however, the bottom-up construction is actually asymptotically faster than inserting n keys into initially empty heap. Okay, that's all they're saying. Okay. This is just the justification. I don't want to read that. Okay, so creating a bottom-up heap construction is faster than just inserting it into a heap. That's very strange. So what they're doing is they're just creating this many heaps, and they're going to combine them together. Alright, let's talk about adaptable priority queues. Alright, so now we're going to talk about the adaptable priority queues. So the functions of a priority queue ADT are sufficient for basic applications of sorting. However, there are situations where you want additional features. Let's say I'm on a standby passenger with a pessimistic attitude may become tired of waiting and decide to leave instead of the borderline. Requesting to be removed from the waiting list. Thus, he would like to remove the entry associated with this passenger from the priority queue. So he just left, right? He decided to leave ahead of the board. Operation remove min is not suitable for this purpose. It only removes the lowest priority. Instead, we want a new operation that removes an arbitrary entry. Let's say another passenger finds her gold frequent flyer ticket and shows up to her agent. Thus, her priority has been modified accordingly. To achieve this change of priority, we would have a new operation that changes the information of a given entry. This might affect the entry's key value or not. So Here's the functions of an adaptable priority queue. The above situations show new areas we want for priority queue. We're modifying, removing specific elements. In order to do this, we need a new way of indicating each entry of the queue is to be affected by the operation. Note that we cannot use the entry's key value because keys are not distinct. Instead, we assume that the priority queue operation insert is augmented so that after inserting the element E, it returns a reference to the newly created entry called position. This position is permanently attached to the entry so that even if the location of the entry changes within the priority queue's internal data structure, position remains fixed in this array. Thus, positions provide us ability to uniquely specify the entry to which each operation is applied. We formally define an adaptable priority queue P to be a priority queue that, in addition to the standard priority queue operation, supports the enhancements. So there's the insert the element E into P and return a position returning to entry. Remove the element in the P and replace E with the element as entry referenced by P and return the position altering their entry. So here's a list-based implementation. In this section, they present a list-based implementation called adaptable priority queue. Their implementation is a generalization of the sorted linked list priority queue implemented. They present the class definition with the exception of the position class, which is presented later. The public part of the class is essentially the same as a standard priority queue interface, which was presented in the code earlier. Except now they have new functions, remove and replace. So, know that the function insert now returns a position, so now they have remove and they have replace. That replaces position. Now they define the class position, which is nested within the public part of the adaptable priority queue. Its data member is an iterator to the STL list. This list contains the contents of the priority queue. The main public member is a function that returns a const reference the underlying element, which is implemented by the overloading the star operator. Here's the position of the queue, the position list, the element at this position, grant access. Okay, so you have star to get the element at the list. Okay. The operation insert is essentially the same as presented in the standard priority queue. Since it is declared outside of the class, we need to provide the complete template specification for the function. We search for the first entry P, whose element exceeds the key exceeds ours. When you insert E just prior to this entry, we then create a position that refers to the entry just prior to P and return it. So you have the insert entry. They have all these find larger element, insert before P, insert position. That's all they do. They find it and they insert it. We omit the definitions of the size, empty, min, remove min. Yeah, okay, so remove they call the erase function. I don't know why. They call erase and then use the insert function. You have chosen perhaps the simplest way to implement the function replace, remove the entry, and then insert the new element E into the priority queue. In general, key information may change, therefore may need to move to a new location in the sorted list. Under the assumption that the key changes are rare, a more clever solution would involve searching forwards or backwards to determine the position possible for a modified entry. While it may not be very efficient, our approach is virtuous simplicity. Okay, let's talk about, let me just search something. Okay, let's talk about location and where entities are implementation. They explain a nice property of the list-based priority queue implementation. In particular, once a new entry is added to the sorted list, the element associated with the list never changes. This means that the positions returned by insert and replace functions always refer to the same element. Note that this same approach would fail if we apply it to a queue-based priority queue. The reason is that a heap-based implementation moves the entries around the heap. When element E is inserted, we return a reference to entry P containing E. But if we were to move it as a result of a subsequent operations applying to the priority queue, P does not change. As a result, P might be pointing to a different element of the priority queue, and attempt to apply remove or replace would not apply to E, but instead to some other element. Solution of this problem involves decoupling positions and entries. In our implementation, adapt queue essentially pointed to a node of a data structure. If we remove an entry, we change the associated pointer. In dealing with the moving entries, each time we insert a new element E into the priority queue, we create a new entry in the data structure and allocate memory for a called locator. Locator's job is to store the current position of the element of the data structure. Each element Each entry of the priority queue needs to know its specified location. Thus, instead of storing the element itself in the priority, we store the location of each element. This is called location aware entry. After inserting a new element in the priority, we return associated location point which points it. Okay, so basically this is just talking about sometimes like when you have like a priority queue, and you insert in something. Sometimes the positions changes, right? It means that the positions returned by insert refer to the same element. Well, that's for priority queue, right? But let's say if you use a heap, like the position changes. Like P does as well. Like it will happen to some other element because of changing the position. So what they're talking about is now instead of doing the thing, they're gonna use a locator to store. Instead of just having the location, they're gonna use a locator, which is to store the locator aware entry. So after inserting a new element in the priority queue, they return the locator object. So how does this solve the decoupling problem? Well, first observe that the user of priority queue wants to locate the position. A previous inserted element. It suffices to access the locator that stores this operator position. Suppose, however, that the entry moves to a different position P prime within the data structure. To handle this, they need to access the location aware entry. To access the locator L, they then need to modify L so that it refers to the new position. So the user may find the new position by accessing the locator. So the price to pay for this generally extra is fairly small. For each entry, they just need to store 2 additional pointers, the locator and locator's address. Each time they move an object in the data structure, they need to modify a constant number of pointers. Therefore, the running time increases just by a constant factor. So whenever you insert a new element in the priority queue, you return the locator object, refers to this pair. So now you want to locate the position of a previously inserted element, just access the locator that stores the position. Suppose, however, the entry moves at a different position in the data structure. To handle this, they access the location aware entry to access the locator L. Okay, how do they implement this though? They didn't even implement it. Well then, alright, that was it. That was all of it. Please rate, comment, subscribe. I was getting tired in the end of this video. But rate, comment, subscribe. Check you guys later. Peace.